right. All right, we're here on part 2 of solving quadratic equations by graphing. And we're going to spend most of our time today dealing with using the calculator here to do this. But let me just remind you a little bit about terminologies. If you need to go back and look at that part 1, please do so. But there is one thing I am going to review. We are looking for there are four names for what we're looking for today. They could be called x-intercepts. Where does the parabola cross the x-axis? Here and here. They also have a name which is called zeros, and the reason they're called zeros is because y is equal to 0 at that point, at that place. See right here, those ordered pairs are something 0 and something 0. So the y is equal to 0 at that place. They could also be called roots, and the reason why we talk about them as roots is I'll share that with you later. And finally, they're called solutions. So when they ask you to solve an equation, they're asking for these 2 points. Now sometimes there may be 2, as we saw in the last, sometimes there may only be 1, sometimes there may be none, because the graph doesn't actually cross the x-axis. Sometimes it sits on the x-axis, sometimes it hangs from the vertex. So this is one solution, 2 solutions, and this one would be no solutions. Okay, does not cross the x-axis. So all of these are things we talked about in the last video. Please go back and take a look at that if that went by you too fast. All right, today we're going to spend some time with some story problems. Let's take a look at your first problem, number 42. Grab your book. We're going to be on page 298, problem 42. All right, problem 42, and several of these problems, I think 43 and 44, are going to talk about this thing with the fall of gravity. Now I mentioned this in the very first video, but we're going to go over it once again because we're going to deal with it here today. On problem 42, they give you this formula. And this is similar, but not exactly the same as the formula I gave you before. This is okay. This is the same formula. There's just a couple things that are omitted here. The height of an object shot or thrown or ejected into the air at a particular time is given by the formula -16 t squared plus v sub o times t plus h sub o. Now you'll notice that these two formulas are the same. Things have been just rearranged a little bit. And the initial height, h sub o, is omitted here. Let me review what all of these things mean. -16 is the speed of gravity. This is gravity. It's how fast things fall. And this is always the same here on Earth. It changes if you go to another planet, obviously, because the gravity pull on other planets is different. T is the time, okay, elapsed after something is shot off or thrown or whatever, after it's shot, okay, after it is shot, okay. V sub O stands for velocity, or that's speed. Velocity is speed. And the 0 here, that's not an O, it's actually a 0. The velocity at the time it's shot off or launched, okay? When the clock starts, what's the speed initially? Now, when you shoot something off into the air, the speed is going to change as it goes higher and higher. It's going to slow down because of gravity. And then as it comes back to the Earth, the speed picks up. But what we're doing with this number here is we're showing the velocity when it leaves the gun or leaves the whatever, the bow and arrow or whatever, when it's shot off, there's a particular velocity, okay? And h sub o is the height of that object at time equals 0. In other words, when it's shot, at the time it's shot. This is t is equal to 0. This is t is equal to 0. When the time is 0, okay? So as you look at this on a picture, you look at this on a picture, if something's shot off into the air, boom, like this, okay? This is going to be h sub o, the height when the time is 0. T is down here, this is time, okay? When the time is 0, that's the height right there. And the velocity is that speed at which we shoot it off into the air. V sub o, that's speed, okay? Now, when we shoot an object up into the air, usually we think of it as going, maybe out at an angle, but it could go straight up or down, it doesn't matter. The gravity acts the same on it either way, whether it's shot forward or shot straight up. And we need to be able to calculate a couple of things. One, find this initial velocity. Well, that's always found right here at the end. That's what we fed. This is the c value. Remember, this is b and this is a. ax squared plus bx plus c. And the initial height is always it's c. It's that initial height right there. And so sometimes our goal in doing these problems is to find the vertex at the top. That's the maximum. Or to find when it hits the ground. When does it land? And that happens to be what we call the 0 or the x-intercept. When does it land? When? And it's going to hit that spot on the ground when the y value is equal to 0. So these are what everything stands for. You take a minute to jot these down so I can move away from this, and then we're going to go ahead and do problem 42. All right. I've trusted that you have written down all of those meanings there. You're going to need to keep those handy. All right, number 42 says an arrow is shot upward with a velocity of 64 feet. Well, the velocity when it leaves the bow and arrow is 64. So that's going to go right here. Actually, let's just use the formula that I had here. I like it better because it's got everything on it. So negative 16 t squared minus the plus the velocity, which is 64 times t plus the initial amount, h sub o. We'll talk about that in a second. Now, let's talk about this number 64. It said it was shot off with an upward velocity. Notice that this number is positive. And you can see that if I shot the arrow up, I would get a different speed of falling than if I shot it down. Well, when this is positive, it means you're shooting it up. If it was negative, you'd be shooting that arrow down. So we're going up, we're shooting up, so it's positive. And so 64 is positive here. It says, ignoring the height of the archer. Well, normally we think of a person standing there and they're shooting off this bow and arrow, right? They're shooting it off. And we usually think of it, of the archer having a certain height, and maybe the bow and arrow is like 6 feet off the ground. But it says in the problem to ignore that height. Ignore that height. So we're going to assume that that arrow is actually shot off from ground level. So this would actually be 0. The initial height is 0. Well, that makes sense because they didn't give us that in the formula here, did they? So the initial height is 0. So I'll put in a 0 here because I'm ignoring the height ignore the height of the archer. Okay? So if he shot it off from 6 feet tall, we'd put 6 in there. If he shot it off from 5 feet tall, we'd put 5 in there. Okay? Now, the question is asking us, how long after the arrow is released does it hit the ground? Well, what it's asking for is, if we think about what's going on here, we're ignoring the height of the archer, shoots it off in the air, and when does it come back to the ground? Our question is, where is that? Well, what that's asking for is the 0, or the root, or the x-intercept. And the y value at that point is 0. Y is equal to 0. So we're going to set this equation equal to 0, negative 16t squared plus 64t. And we're going to go ahead and we could do this with our pencil, but we're going to do it with the calculator. So go ahead and put this in your calculator, and we're going to find where it hits the ground again. Okay, so we've entered that in the calculator here. And this, of course, this graph represents the full arc of this graph. And when we put a 0 in for y, we're going to want to figure out where it hits the ground. But it's all those dots, all the dots on the graph. By the way, make sure that you have a negative up here and not a subtraction sign. If you put a subtraction sign here, it'll probably give you an error message. Let's go ahead and zoom standard and see what happens. Okay, well, this graph is pretty steep. It's hard to see what's going on, but we do notice that it went through here. I'm going to change my window because I don't need to see all of this stuff where x is negative, so I'm going to change the window so that my x minimum is, say, -2, and graph it again. You can go ahead and do that too. Okay. Now also, it would be nice if I could see the top of this graph. So let's go ahead and change the window setting to Y max. So I'm going to go Y max. Let's put 200 in here. I don't know if that's too high or right, but let's go ahead and graph it. There we go. That's probably higher than needed. Let's change that to 100. So I'm going to change my Y max to 100, and I get a good look at my picture. By the way, you'll notice that when I do this, I try to make it so that my picture is fairly understandable and it's not too big and not too small. There's one last thing I'm going to change. You'll notice all of these little marks over here. They're too close together. So I'm going to change my scale on the y-axis. The x scale looks pretty good, but let's change the y scale. So I'm going to go Window. Let's change my y scale. If I'm going all the way up to 100, if I divide that by, say, 10, that gives me a tick mark every 10 units. 10 divided into 100 is 10. That'll give me my tick marks, fewer tick marks, and it should look a little bit better. So change my y scale to 10. I'm going to leave the x scale the same. There you go. Now my scale looks pretty normal, and I can see from my picture that it goes up 1, 2, 3, 4, 5, about 6, somewhere between 6 and 7. That'd be somewhere between 60 and 70 feet high. I can see that. Okay. Now, if we wanted to, it didn't ask us for this, but if we wanted to, we could find that spot at the top where the maximum height was, and on subsequent chapters we're going to do that. But what it did ask me is, when does it hit the ground? And as I look over here, it was at the ground right here. Well, we knew that. It was at the ground when the clock started at 0. And as the clock is moving to the right, 1, 2, 3, 4 seconds, it looks like it hit the ground at 4 seconds. And so I might just write the answer 4 down, but I want to check with my table, because maybe the graph is a little inaccurate, not inaccurate, but it's not detailed enough. Maybe we're too far away, and maybe it's 4 point something. So let's go look at tables. So I'm going to go second table and look at my graph, and I see here right here that in fact it was at ground level 0 when time was 0. X is time here. And it returned to ground level 0 when time was 4. And I think we're in seconds here. We'd have to be, because this formula for gravity is in seconds. Okay? So we can answer the question, it hit the ground again at 4 seconds. So the answer to number 4 is 4 seconds. It took 4 seconds to hit the ground again. All right, let's take a look at the next problem. All right, we'll take a look at problem number 43. I've got the formula up here. You'll need to memorize this formula. This is something that not only comes in handy here, but you get to physics, you'll probably have to review this formula. Just want you to know, we're going to plug stuff in for V, for h and for h of t. So we're going to plug 3 places in. We're going to plug something in here, here, and here. And if they give us the time, we're going to plug the time in too. But most of these problems, they're asking for the time when something hits the ground or when it's at a certain height. Let's look at 43. A tennis ball is hit upward with a velocity of 48 feet. Well, upward means that this has to be positive 48 feet per second. 48 feet per second. Notice we're in feet and we're in seconds here. Okay? Ignoring the height of the tennis player. So once again, the tennis ball, you would normally think of hitting that ball at about waist high. We're going to ignore that and not call it 3 feet. We're going to ignore the height of the tennis player and call it 0. And now it asks the question, how long does it take for the ball to fall to the ground? It's hitting it upward at a velocity of 48, straight up, the velocity of 48 feet per second. So when does it hit the ground? It's right here. This is the ground when it hits. Okay, and over here is when it is struck by the tennis racket. Okay, hits the ground, the height is 0. Struck, it was at the ground. Okay, it was struck here too. And this is the speed when it was struck. This is the height when it was struck. This is when it hit the ground. So we're going to go ahead and put that in our calculator again. Let's do that. All right, so I've entered that in here. I mean, if I wanted to, I could put plus 0 out here, but that isn't going to do anything to the equation. But that does show me that the initial height was at 0. Let's go ahead and graph this. So I'm going to hit zoom standard and see what we get. And as expected, it did cross through the 0, 0 here. But I got the same kind of issue with seeing my graph. So I'm going to go change my window. Let's change it so my x minimum is -2 again. I could make it 0, but I want to be able to see that y-axis. Let's change my y-max to maybe 100 again. And let's change our y-scale to maybe 10 again. Same numbers we had last time. Let's graph it. Here we go. I didn't probably have to go that high, so I could change my window to, oh, I don't know. Let's change my y-max to maybe 50. That's probably high enough. There we go. So I can see, looking at this picture, that the tennis ball was struck when time was 0. It went up 10, 20, 30 some feet, hit a top up here, and then it came back down and hit the ground here. Now that looks like it hit the ground at 1, 2, 3 seconds, but I want to go ahead and look at my table. So here we go, second table, and sure enough, it was at ground level when time was 0, and it hit ground level again, 0 at 3 seconds. So my answer here is simply 3 seconds. See how easy these are? You just need to look at the y column to see when it's 0, and then check over for the answer in the x column. Let's look at 40. All right, number 44, basically it's the same problem. Okay, same formula. A boat in distress launches a flare straight up with a velocity of 190 feet per second. Ignoring the height of the boat, how many seconds will it take for the flare to hit the water? So once again, it hits the water at 0 feet. That number doesn't change, and the upward velocity here was 190 feet per second. And we're ignoring the height of the boat, so that's going to be 0 as well. I'm going to let you do this one to finish it. Go ahead and find how long it takes for that flare to hit the water. Let's take a look at number 45. All right, number 45 is not about gravity. It's got another application here. Let's take a look at it. Law enforcement. Police officers can use the length of skid marks to help determine the speed of a vehicle before the brakes were applied. If the skid marks are on dry concrete, the formula s squared over 24 equals d can be used. Let's jot that formula down. S squared over 24 equals d. Okay? Okay, now what does everything stand for here? In the formula, S represents the speed in miles per hour. S is the speed of the vehicle in miles per hour before they hit the brakes. Okay? And D represents the length of the skid mark. Length of skid mark. Okay? Now the question's asking, okay, if the length of the skid mark on dry concrete are 50 feet, how fast was the car traveling? Well, that's pretty simple. Let's just go ahead and put 50 feet in here. The skid mark is 50 feet long. We'll put 50 in here. And if we're going to solve this, we're going to set this equal to 0. I'm going to write 1 over 24, and I do that just because it just helps me see that this is A, minus 50 equals 0. Now you notice I set it equal to 0 because we're trying to solve this equation to find out how fast the car was traveling. Now if you put this in your calculator and want to find out how fast the car was traveling, when the car, you know, at that initial moment when you hit the brakes. So let's put that in the calculator and see what happens. By the way, you could just leave this as s squared over 24. It's probably easier to put it in your calculator if you remember to put something in parentheses. So let's do that. Let's put it in the calculator. Alright, now I've entered this in the calculator, and it turns out I really didn't need these parentheses here because I was just subtracting after that. Let's go ahead and see what happens, and this is where your understanding of the calculator and understanding about what everything stands for is important. Okay, so let's go ahead and I'm going to hit zoom standard. Watch what happens. And now it's done working. I can see looking up here that it's done working, but I got nothing on the graph, and so I don't know what's going on here. Well, I'm going to have to cue in on this equation a little bit. Can you tell anything about where this picture is looking at this equation? Well, we know that this number out here is C. A is 1 over 24. B is not here at all. But C is negative 50. And C is the y-intercept. So I'm not going nearly low enough on my graph. I've got to go way down here. I've got to go down. So I'm going to set my window to go down to y minimum at least to 50. Let's go to a negative 60 there and see what happens. I went down to a negative 50 and see if I can see that. Here we go. Yeah, there's the parabola. It's down right where we expected at a negative 50. Now I'm going to change the scale first, and then I'll come back and change something else. Let's change the scale on the y-axis. Let's change the scale. Since I got to go down to 60, let's make it go by 5s. That might be a little better, and graph it again. There we go. So now I can see, by counting them here, I've got negative 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. Yeah, that's negative 50. That's right. So this is my parabola on this, and you'll notice that this parabola is very flat. And there's a reason why it's flat, and we'll talk about this a little bit later, is this equation has an a value of 1 over 24. It's a fraction. It's a small fraction, in fact. And fractional a values cause the graphs to flatten out a lot. Okay, so this has been flattened. If that number a value was very big, it would be a very tall, skinny graph. But because the a value is a small fraction, it's caused our graph to be pretty flat. So there you see the graph, and it's pretty flat. Now, remember, we're trying to solve this, and I need to know where it crosses the x-axis. Well, it looks like it's going north here, and here it looks like it's going north too. But I don't actually care about this back here because this is going back in time. So I don't care about this. I want to go forward in time. So I'm going to change my window so that I don't see all of this back here. I'll chop it off at like at -2. But I got to go far in the future. And in fact, if I project this out here, I probably got to go out to like 40 or 50 because that's what this guy's speed is probably. So we know his speed might have been higher than that, but let's go change the window. I want my x minimum to be something not so far to the left. Let's put -2 in there. And I want my x maximum to go farther to the right. Let's put 50 in there. And since I'm making a scale going up to 50, I think I'll make my x scale go by 5s. Okay, and let's graph that. All right, yeah, there it is. In fact, that makes pretty good sense here. So he hit the brakes and he slowed down, and the length of the skid marks are telling me how far before he comes to a complete stop at 0. Okay, and it looks to be about 5, 10. Remember, I counted these by 5s. 5, 10, 15, 20, 25, 30, 35 or so, but it's not right on that mark, it looks like to me. So I'm going to go look at table. Let's go look at table. Second graph. And I can see from the table that I don't have y at 0. So I got to go way down here on my table. But you know, I mean, I could do that. I could arrow down on this table and keep going, and it's going to take me a long time to get there. But you know, there's another way to change my table setting, and I'm going to show you how to do that again. I'm going to go second window, which is table set. And instead of starting at 0, or in this case 4, I'm going to start at something closer to where my answer was. And I think the answer was near 35. So I'm going to put 30 in here, and I'm going to go by 1s again. Okay, still go by 1s. And we're going to go ahead and look at the table now. Now you'll notice that my table is starting at 30. Starting at 30 right here, okay? And it's going forward from there. Now what's happening at y? Well, remember we said that when the sign changes, that's where it crossed the x-axis. So look right here, it's negative, 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 and then eventually right here, it turns to positive number. So between these two numbers, 0 occurs in here. So now I'm going to look at the x column. It's going to be between 34 and 35. So the answer is somewhere close to 35, but it's also probably close to 34. Now if I want to get a more accurate answer here, I'm going to start my table at 34 and go by smaller increments. Let me show you what I mean. Second table step. Let's start at 34 and go by tenths, like 0.1, and see what the table says. See, now I've started at 34, but I'm going by 0.1s, so I can see a little bit more accuracy here. And I notice that it changes from negative to positive between 34.6 and 34.7. So somewhere after 34.6, it must be 0. If I even want it more accurate, I'll start at 34.6 and go by hundredths. Let's do that, okay? Let's go to 34.6 and go by hundredths, 0.01. What I'm doing is I'm trying to improve the accuracy. Let's go ahead and look at the table. And now I can see I started at 34.6 and I went by hundredths, and it changes signs right about here, right here. And so it's somewhere between 34.64 and 30.65. It changed signs. So once again, you're looking for where does the sign change. So my answer here is about 35, but if I want it more accurate, I'd say about 34.64. So my accuracy is about 34.64. And that would be the speed at which this guy was traveling when he hit the brakes. So my answer is about 34.64. Your book says 35, but I showed you how to get it a little more accurate. Come back and take a look at how I did that by adjusting the table. Here, you can tell when the sign changes in the y column. See, the sign changed in the y column. Here the sign was like negative, and then it changed to positive. And when that sign changes, we know that it's somewhere between these two numbers. So it's about 34.64 plus a little bit. And if I wanted it more accurate, I would just adjust the table again to start at this number and go by maybe thousandths instead. Now, that skill is an important skill to learn, to be able to get your answer a little bit more detailed. So go back and practice that. Look at it again and practice that a few times. All right, these videos were extra long. This section, 6-2, is the most important section in this chapter. So we spent 45 minutes on the last assignment, or a video, and 30 on this. So you spent an hour and a half on this, but this is a very important section. You may have to watch them again. All right, here's your homework for tonight. All right, so here's that assignment for tonight. I gave this to you in the last installment here, but again, page 297, giving you some more even problems to practice on. Use the table feature of your calculator to find zeros or estimates. I've also given you a problem 46 to do, so you've got to finish 44 on your own and also do number 46. You'll notice that problem 46, they give you an initial height, and the initial height of the Empire State Building was like, I don't know, is that in feet? Yeah, 1,050 feet. You got to put that in there as well. So you can do those problems. Please take your time on this. This is a very important section, and it's kind of a critical aspect of this whole thing on quadratics. Hey, enjoy yourself. Sorry these videos took so long, but you guys are doing great. See you later.